Okay, this is USF TTE4004, help session number 1. These are some problems related to mostly braking and reaction time. So the first problem is shown here. The vehicle is initially traveling 60 miles per hour, skids to a stop on a 3% downgrade, and the pavement provides a coefficient of friction equal to 0.3, and the question is, how far does the vehicle travel before coming to a stop? So we know that the initial speed is 60 miles per hour. We know that G is minus 3%, so that's 0.03, and F is 0.3. So we would like to know the total braking distance, which we call d sub b. So the solution for this, d sub b equals v initial squared minus v ending squared divided by 2g lowercase g times f plus or minus capital G. So in this case, we know that v sub I is 60 miles per hour, and v sub e is 0 because the vehicle is stopping. Lowercase g is the gravity deceleration, 32.2 feet per second squared. We also know that the friction factor is 0.3 and capital G is a negative 3% or 0.03. So I'm going to write those items as I just stated. Okay, so I've used dimensional analysis here, as you can see, which I'll always try to do just to help everyone keep the units straight. The units in this portion of the denominator are non-existent. They're both unitless ingredients. So if we multiply the numerator and the denominator through, the units are feet squared per second squared. In the numerator, and in the denominator, the units are feet per second squared. So if we perform that calculation, we should receive about 445.4 feet. So this is the solution to problem number 1. Okay, here is question 2. We are given v sub I is 90 miles per hour. G is minus 0.03. And the braking distance d sub b is 650 feet. So for this one, we'd like to find lowercase f, which is the friction factor. So we use the same equation, d sub b equals vi squared minus ve squared divided by 2g times f plus or minus g. And again, ve is 0 because the vehicle is stopping. So using dimensional analysis again, 90 miles per hour times 5,280 feet per mile times 1 hour is equivalent to 3,600 seconds squared minus 0 squared. And in the denominator we have 2 times 32.2 feet per second squared times lowercase f minus 0.03. So 3% downgrade, 3 divided by 100 is 0.03, and it's downgrade, so it's a minus in this case. So we can solve this equation for lowercase f. So as you can see here, I've just I've equated the formula to 650 feet, which was the distance that the vehicle took to stop. And I just multiplied through in the numerator, 17,424 feet squared per second squared. I multiplied through in the denominator Then I cross multiplied, so 17,424 feet squared per second squared equals 41860 times F minus 1255.8. So that's a constant. So we can just bring this to the other side and divide both sides by 41,860. And in this case, for problem 2, friction factor is equal to 0.45. And now example number 3, what is the grade for the previous example if the coefficient of friction is 0.40? So as you can see, these questions can have different unknowns. So I'm just going to go back and use the numbers that I had before, 17,424 feet squared per second squared divided by 2 times 32.2 feet per second squared, and insert lowercase f 0.40 minus g. So remember in the previous example, the slope was downhill. So I'm going to assume that the same thing applies. So solving this problem now, G equals minus 0.016, and you can multiply that by 100, it's minus 1.6%. So because the G in this case came out to be negative, my assumption that it was a downgrade was incorrect. So what this really means is a 1.6% upgrade, right? So that's the solution to this particular question. Okay, so this is question number 4 from the help session, and this is accident reconstruction, crash reconstruction. So first we're going to take the average of the skid mark lengths. Skid marks show when the vehicle was actually engaged in braking. We're going to calculate the friction coefficient, and then we'll calculate the unknown initial velocity. So to calculate the mean value of the skids, we have 4 skid values, 680. So the mean value is 655 feet, so that's what we'll use. And since we had a trial run to help measure the coefficient of friction, we'll use the data from that. We'll use the 35 mile per hour example to calculate the friction factor. So we're just going to use the same equation that we've been using for the braking distance. So this is the initial speed of 35 miles per hour, and using dimensional analysis again, 5280 feet per mile and 3600 seconds per hour squared, and then the vehicle is stopping, so the ending speed is 0, and then 2 times 32.2 feet per second squared times f, and we assume that this is level ground, and I guess it doesn't really say, so you would want to make that comment in your solution. And so the braking distance is 325 feet. So we can now solve for lowercase f by multiplying 2 through 2635.11 is the numerator, divided by 64.4 f. And of course this is in feet squared per second squared, and this is in feet per second squared. And that's 325 feet. So we can solve this for the unitless. The units will all cancel out, and f is 0.13. So that's basically step 2. This was step 1, step 2, and now step 3 is to calculate the unknown initial speed using the data that we already have. So v sub I, using the same equation, and that's in, we would like that to be in miles per hour. And so in order to convert it to feet per second, so we know in this case that the vehicle hit the pole at 30 miles per hour, so the ending speed is 30 miles per hour. So both of those are squared. And then in the denominator, 2 times the deceleration of gravity times our friction factor. We just calculated 0.13, and since this is assumed to be on level grade, g will be 0. And so we know that the distance was 655 feet, because that's the skid distance. So now we can solve for v sub I. So this is going to be 2.15 vi squared minus 1936 equals 548.66. So this is, of course, these feet per second, hours, mile, mile. Feet squared per second squared. And because we had this cross multiplication, this is also feet squared per second squared. So the units are consistent. So vi squared is 3451, and vi equals 58.7 feet per second squared. And then we would like to present velocity in miles per hour, so we can multiply times the inverse of what we were doing upstairs, 3600 seconds per hour, times 1 mile divided by 5280 feet. So the feet cancel out. Sorry, that's seconds cancel out. So we have miles per hour. So it is 40 miles per hour, which is our solution. So this one was a little bit more involved. This is question 5. Determine the stopping sight distance from example 4 just above, assuming an AASHTO recommended perception reaction time of 2.5 seconds. So we've been focused till now on the braking distance. Now we want the total stopping sight distance that includes the perception reaction time. So d sub s is d sub r plus d sub b. And so the perception reaction time, the time it takes to travel while perceiving and reacting, is just the speed times the perception reaction time. Call that v sub I times t sub r, plus the equation we've been using. Okay, so we have the values from the previous example. So we know that the vehicle was traveling 40 miles per hour for 2.5 seconds. So we have to convert as we've been doing. 5,280 feet per mile and 3,600 seconds per hour times 2.5 seconds. Miles cancel out, hours cancel out, seconds cancel out. So this is now all in feet. And the second part of the equation is 40 miles per hour times and the ending speed is 0, and this is 2 times 32.2 feet per second squared times our friction factor, 0.13, that we calculated earlier. And it's a flat grade, so G is 0. So if you perform these calculations, you should find 147 feet for the perception reaction distance, plus 413 feet for the braking distance. So the total should be 560 feet for the stopping sight distance. So that's example number 5. So I didn't write this question, and I apologize, it's a little bit morbid, but you see something in the road and you need to stop. So this is just another example. Your vehicle was initially traveling at 100 kilometers per hour and skids to a stop on a 2.5% upgrade, so the road is going up. And you take 75 meters to do so. What was the coefficient of friction on this surface? So the only difference about this problem is we're using SI units or metric units, but the procedure is exactly the same. We're back to just the braking distance. So the braking distance in this case is the initial speed, 100 kilometers per hour. And we would like to, since we have the distances expressed in meters, we'll convert kilometers to meters. There are 1,000 meters in 1 kilometer. So using dimensional analysis, there are 3,600 seconds in 1 hour. The ending speed is also 0 since we're stopping. And then in the denominator, the deceleration of gravity using SI units is 9.8 meters per second squared. Then we're looking for F, and then this is a plus 2.5%, so you divide 2.5 by 100, and we have a plus 0.025 in the denominator. And we know that the braking distance actually accomplished was 75 meters. So we can simplify this. I'm skipping a few steps. So this is in the kilometers cancel out, the hours cancel out. So we have meters squared per second squared. And in the denominator, we have meters per second squared times something unitless. And so we can simplify this and calculate. This is meters, so everything canceled out. Meters, we want the left-hand side to be unitless. So the friction factor, which is the answer we're looking for, is 0.5, and that's how you handle that kind of a problem. Okay, so now this is question number 7, and the only difference here is the use of the phrase practical stopping sight distance. So we're going to follow a slightly different procedure from the Mannering book using equation 2.47, which is the stopping distance is equal to VI squared divided by 2 times G times A over G plus or minus G, capital G. So this will use, for lowercase a, the AASHTO recommended deceleration rate, which is 11.2 feet per second squared. So that's the only difference. So I'm just going to, so the question is to compare two different drivers. Each one has a reaction time of 2.5 seconds. One is traveling at the speed limit, 55 miles per hour. The other is traveling illegally at 70 miles per hour. So the point here on a 2.5% downgrade is to compare the total stopping distance, just to kind of wake you up to how much a small, relatively small increase in speed will have on the total distance required to stop. So for driver number one, we're just going to do the calculation for the total stopping distance. So that's the equation for each one of these. So for driver number one, traveling the speed limit, 55 miles per hour. Times 2.5 seconds. Okay, so that will, these will all cancel out. So you'll have feet, which is what we want for the distance, and then that will be 202 feet. And then the second half, it's again 55 miles per hour. It's 5,280 feet per mile. Times 1 hour divided by 3,600 seconds squared. So the ending speed is 0, so we're just going to leave that off. Then 2 times 32.2 feet per second squared. And this is 11.2 feet per second squared divided by lowercase g, 32.2 feet per second squared. So those, of course, cancel out. And here we have a 2.5% downgrade. So 2.5% divided by 100 is 0.025. And if you perform those calculations, you should find that that braking distance is 313 feet. So the total stopping distance is 515 feet. Now I'm going to do the same thing for driver number 2. So as you can see for the second driver, because the speed is higher, the distance traveled during perception and reaction is 257 feet, and the distance traveled while braking is 507 feet, for a total of 764 feet. And the difference between the two is 249, or about 250 feet. So the point is here, you can compare the impact that exceeding the speed limit has on the ability for a driver to stop for any kind of obstruction in the road or for any purpose. Okay, here's another question using practical stopping distance. So we will again use the equation that we used earlier with the AASHTO recommended deceleration rate of 11.2 feet per second squared. And this is the main goal of this question, is to compare from an experiment how well drivers can react when sober and when impaired. So this will just compare the difference in reaction time. So the first example is in the sober case. We know the total stopping distance is 385 feet. What we don't know is the reaction time. So we have enough information to calculate the reaction time using our stopping distance equation. So in the first case, well, both cases, the vehicles are traveling at 50 miles per hour. So you can start with the perception reaction distance, 50 miles per hour times 5280 feet per mile times 1 hour divided by 3,600 seconds times TR, which we don't know in this case. We're solving for, plus 50 miles per hour times 5280 feet per mile times 1 hour divided by 3,600 seconds squared. And again, the vehicle stopping, so the ending speed is 0. So we're using that practical, it's a level pavement, so we don't need to worry about the grade. 32.2 feet per second squared times 11.2 feet per second squared. That's the AASHTO recommended lowercase a. And since g is 0, that's all we need to do. So these cancel out. So we know that this is equal to 385 feet. So we can solve for t sub r, 73.5 t sub r plus 241.17 equals 385. So t sub r in this case is 1.96 seconds. So the reaction time actually seen in this experiment is shorter than the standard AASHTO 2.5 seconds. And it is the case that people do perceive and react in a shorter time than 2.5 seconds. So in this case, the sober driver is doing okay. So what happens when the driver is impaired in this experiment? We expect that the perception reaction time will increase, and we just want to know by how much. So I'm going to follow the exact same procedure. In this case, the ending speed is 30 miles per hour, and I'm going to show you how to do those calculations now. Okay, so I repeated the same procedure using the ending speed of 30 miles per hour. I'm sorry, I ran out of room here on the right-hand side. But there's really nothing different about the procedure except that the ending speed was not 0. We're again solving for t sub r. And so doing the math, we know that the total stopping distance was 385, or the total distance was 385. Of course, the vehicle was still traveling 30 miles per hour when it hit the object. And in this case, the perception reaction time turns out to be 3.14 seconds, which is, of course, more than the 2.5 standard value that we use in practice. So it's important to remember that with impairment, which certainly causes a lot of crashes today in the United States, a big problem, a big issue is that the perception reaction time of an impaired person is much larger, and our road design is not equipped to handle that. As you know, practice makes perfect. So here's another problem. Looking at an object that enters the roadway. In this case, it's assumed to be a child. It could be anything. The vehicle is traveling at 40 miles per hour with a level road. So what distance in advance should the driver see this object? And this comes into play when you're designing road signs, when you're making decisions about landscaping or parking. So how can you make sure that the driver has a clear view for this particular speed for a certain distance along the road? So the total stopping distance, again, is the perception reaction distance plus the braking distance. And in this case, we start with 40 miles per hour. Time, we'll use 2.5 seconds. And then again, so the ending speed is 0. And this is not a practical stopping distance question. This is just a stopping distance question. So we'll go back to the original formula that we had. Using a friction factor of 0.32. And the friction factor, so in the notes, I provided this table, this AASHTO table. And so you can use these numbers for 40 miles per hour. You can see that the coefficient of friction would be 0.32. So that's what I'm doing for this example. So if you perform the calculations, the distance traveled as shown in the table during perception reaction is 147 feet, and then 167 feet while braking. So the total distance in advance that you need is 314 feet. So that's the answer. So here's problem number 10. And the point here is just to look at the impact of grade on total stopping distance. Obviously, if you're going downhill, it's going to take you longer to stop than it will when you're traveling on a level surface. So that's what this problem is aimed at looking at. So we can calculate the stopping distance for level ground first, and then so this is including perception reaction time. So the d sub s equals the distance traveled during perception and reaction, which is 50 miles per hour, times 5280 feet per mile, times 1 hour is equivalent to 3,600 seconds, times 2.5 seconds. That's the plus the braking distance, squared, and the ending speed is 0. So for this problem, I'm going to use the friction factor for 50 from this table, which is 0.3. And then it's level ground. So this is 183.8 feet plus 279.6 feet. So the total stopping distance is 463.4 feet. So now I'm going to do the same thing for the 3% slope. So the procedure for the second part is exactly the same. The only difference is we include the slope. So this is a downhill 3%. 3 divided by 100 is 0.03. Please don't forget that. And so the distance, the braking distance goes up from 279 to 310. The distance traveled during perception reaction stays the same. The total stopping distance on the downhill is about 495 feet. And if you subtract 463 from 495, you get about 32 feet longer. So simply the addition of the 3% downgrade increases the total stopping distance by 32 feet. Okay, so this is the last problem, number 11. And it's kind of a crash reconstruction or crash analysis. So I'm just going to draw a little bit of a sketch. You could imagine that there was a barricade and then traffic is moving in this direction. And so about 1,000 feet before the barricade, there was a sign number 1, and a second sign about 600 feet. So this is 1,000 feet, and this is 600 feet. Those are the signs. And then the skid mark is 300 feet long. And so what we want to do is try to determine whether the driver saw the signs. Clearly the vehicle traveled 700 feet, 1,000 minus 300, before initiating braking. Chances are that the driver didn't see that sign, but we can calculate the perception reaction time. From the perspective of the first sign at the speed limit. So the speed limit was 55 miles per hour. So how would you calculate the reaction time? So the 700 feet of distance divided by the speed limit. So this was about 8.6 seconds. So the driver had about 8.6 seconds that they traveled from the first sign to the point where they hit the brakes. This I just used dimensional analysis. So the feet cancel out and the seconds move up to the top. So we can conclude that the driver didn't see the first sign. Let's try the same thing from the second sign. So the driver traveled 300 feet before initiating braking. So same, assuming the speed limit. So this one is 3.7 seconds, so both of these are greater than 2.5. So chances are that the driver also missed the second sign. So what we would like to do is calculate or estimate the speed that the driver was actually traveling. And so we can do that using our braking distance equation. Since we know that the braking distance of 300 feet, we don't know what the initial speed was. And we were told that the speed that the driver hit the barricade was at 25 miles per hour. And we were also told that the friction coefficient would be 0.3. So on level ground, we have all the information that we need to solve for VI. So just to wrap up this last part, I just carried through the calculations here and solved for V sub I. And I tried to emphasize the units. So V sub I squared equals 7,140 feet squared per second squared. So when you take the square root of both sides, you get V sub I on the left, and then 84.5 feet per second on the right. But please remember that we like to express speed in miles per hour or kilometers per hour, whereas usually we express distance in feet or meters. So we have to convert this feet per second, just like we've been doing So in order to cancel out the feet, using dimensional analysis, 1 mile is equivalent to 5,280 feet, and 3,600 seconds is equivalent to 1 hour, so the seconds will cancel out, leaving us with miles per hour. The result for V sub I is 57.4 miles per hour, which is a little bit over the speed limit, so if we were going to testify to the jury, we would say that the driver was indeed speeding in this case. So thank you for listening.